Good morning, students. Welcome to Heat and Mass Transfer class. Today, you are going to learn about convection. Convection. Convection is a process of heat transfer that will occur between a solid surface and a fluid medium. So, examples: heat transfer from heater to room air and cooling of hot tea. Natural convection. So, if the fluid motion is produced due to change in density resulting from temperature gradients, this mode of heat transfer is free convection, otherwise called as natural convection. Forced convection. The fluid motion is artificially created by means of any external force like blow air or fan. Then the mode of heat transfer is known as forced convection. The Newton's law of convection states that the heat conduction is directly proportional to surface area and the temperature difference between surface to surrounding fluid. That means Q equal to HA into Ts minus T infinity, where H is convective heat transfer coefficient, AS equal to heat transfer surface area, then Ts temperature of the surface, T infinity is fluid temperature. The Nusselt number is defined as the ratio of heat flow by convection process under an unit temperature gradient to the heat flow rate by conduction under an unit temperature gradient through a stationary thickness of L meter. That means Nu equal to HL by K, where H is convection heat transfer coefficient, then L length, K is thermal conductivity. The Nusselt number is a convenient measure of the convective heat transfer coefficient. For a given value of the Nusselt number, the convective heat transfer coefficient is directly proportional to thermal conductivity of the fluid and inversely proportional to the significant length. The Reynolds number, it is ratio of inertial force to viscous force, Re equal to UL divided by nu, where U is velocity, L length, then nu kinematic viscosity. Reynolds number is therefore a measure of relative magnitude of the inertial force to the viscous force occurring in the flow. Then Prandtl number, it is ratio of momentum diffusivity to thermal diffusivity. PR equal to nu divided by alpha, where nu is kinematic viscosity, then alpha thermal diffusivity. Prandtl number provides a measure of the relative effectiveness of the momentum and energy transport by diffusion. Grashof number, it is defined as the ratio of product of inertial force and buoyancy force to the square of viscous force. So Gr equal to G into beta L cube delta T divided by nu square, where nu is kinematic viscosity, then beta coefficient of expansion, then L length delta T temperature difference. Grashof number has a role in free convection similar to that played by Reynolds number in forced convection. Stanton number, it is ratio of Nusselt number and Prandtl number. Stanton number equal to H divided by rho U into Cp, where H is convective heat transfer coefficient, rho density, U velocity in meter per second, then Cp specific heat capacity at constant pressure. Next, Newtonian and non-Newtonian fluids. Newton fluids which obeys the Newton's law of viscosity. The non-Newton fluids which do not obey the Newton's law of viscosity. Laminar flow. Laminar flow is sometimes also called streamline flow. In this type of flow, the fluid moves in layers and each fluid particle follows a smooth and continuous path. The fluid particles in each layer remain in an orderly sequence without mixing with each other. Next one, turbulent flow. It is a distinct irregular flow, is frequently observed in nature. This type of flow is called turbulent flow. The path of any individual particle is zigzag and irregular. That means layers are mixing with each other. Velocity bound layer. Consider a parallel flow of fluid over a flat plate. The velocity of the particles in the first fluid layer adjacent to the plate becomes zero because of no slip condition. This motionless layer slows down the particles of the neighboring fluid layer as a result of friction between the particles of these two adjoining fluid layers at different velocities. This fluid layer then slows down the molecules of the next layer and so on. Thus, the presence of the plate is felt up to some normal distance delta from the plate, beyond which the free stream velocity u remains essentially unchanged. As a result, the x component of the fluid velocity u will vary from 0 at y equal to 0 to nearly u at y equal to delta. The thickness of the boundary layer, distance from the plate boundary surface and surface at which the local velocity or temperature reaches 99% of the external velocity or temperature. Thermal boundary layer, the flow region over the surface in which the temperature variation in the direction normal to the surface is significant is the thermal boundary layer. Okay students, so that's all today. Thank you.